This is Richard Hammack's Calculus 1 course. We're in Part 1, Function Review. Today, Lecture 5a on exponential functions. This is the first in a sequence of 4 lectures, 5a, 5b, 5c, and 5d, on the basics of exponential and logarithm functions. So today's short lecture is just on exponential functions. Today's plan is to, first of all, review exponents, and then review exponential functions. And I might add that much of what we do today you should already know and do already know, but it's good to have a refresher. Let's start with the review of exponents. If a is a number and n is a positive integer, you know that a to the power of n is a times itself n times. So for example, 2 to the 4th is 2 times itself, 4 times, 2 times 2 times 2 times 2, and that's 16. If you had 2 to the power of 1, that would just be 2, so that would just be 2 to the power of 1 equals 2. And in general, a to the power of 1 equals a. Now, from this basic definition, a lot of things will flow, and we're going to collect some basic properties of exponents that I'm going to put into this blue box. The first one being a to the power of 1 equals a. Think about taking a times b and raising it to a positive integer power. That would be ab times itself n times, by definition of ab to the power of n. And you could collect those n a's together and the n b's and group them together. This would be equal to a times itself n times, then times b times itself n times, and that's a to the n times b to the n. So our next basic property is ab to the power of n equals a to the n, b to the n, right here. You could also do a over b to the power of n, and that's just a over b times itself n times. And if you do that, you have a times itself n times on top, that's a to the n, and b times itself n times on the bottom, that's b to the n. So our property here is a over b to the power of n is a to the power of n over b to the power of n. This should all be familiar to you. If ever you have a to the power of m times a to the power of n, that a to the power of m is a times itself m times, and then it's multiplied by a to the n, which is a times itself n times, and altogether you have a times itself m plus n times. So a to the power of m times a to the power of n equals a to the power of m plus n. We'll record that right here. Let's see. Let's also think about what a to the power of m divided by a to the power of n would be equal to. And for the moment, think about m and n being integers where m is bigger than or equal to n. So you have more a's on the top. You'd have a times itself m times on the top divided by a times itself n times on the bottom. So these n a's on the bottom would cancel out n of the m a's on the top, and that would leave you with a times itself m minus n times. And we get an answer of a to the power of m minus n. So a to the m divided by a to the n is a to the power of m minus n. That's our next property. Finally, think about a to the n, whole thing raised to the power of m. That would be a to the n times itself m times, and a to the n is a times itself n times, giving you a times itself n times multiplied by itself m times. How many a's do we have altogether? Well, m times you have n a's, so that's a total of a times itself n times m times. So a to the n to the power of m is a to the power of n times m. and we'll record that. So these are basic properties of exponents. And I think you're very familiar with these. They become so automatic that sometimes you forget where they come from. So I'm hoping that the derivations on this page will remind you that these laws, these properties, are very commonsensical. Now, as we've stated them, n here and m, the exponents, those are integers, positive integers, in fact. But you probably have a hunch that all these properties hold for m and n just being real numbers, and that's the case. And I'm going to talk a little bit about how these basic exponent laws in the blue box expand to more general laws. Summarizing what we had in the blue box, here are all the basic laws of exponents. And think of them still as m and n, just positive integers. What about if you had a to the power of 0? Well, a to the power of 0, you could think about that this way, that 0 is 1 minus 1. So it's a to the power of 1 minus 1. And using this property, a to the power of 1 minus 1 would be a to the power of 1 divided by a to the power of 1. And that's equal to 1. Actually, it equals 1 as long as a is not equal to 0. Otherwise, you get 0 divided by 0. So the takeaway here is it's very commonsensical. A to the power of 0 has to be equal to 1. It's inescapable. So a to the power of 0 equals 1 if a is not 0. Otherwise, it's not defined because you get 0 divided by 0. So that's a new property. We always know that a to the power of 0 is equal to 1. What about a raised to a negative power? Now, of course, previously we defined a to the power of n as a times itself n times. That doesn't make any sense if n is negative. But from these basic rules that we have, you can deduce what a to a negative power would have to be. A to the power of minus n, well, that minus n is 0 minus n. And if we are to believe this property, a to the power of 0 minus n would be a to the power of 0 divided by a to the power of n. And a to the power of 0 we know is 1. So a to the power of negative n equals 1 over a to the power of n. That's a basic property. And we'll put this in our box up here. So notice how we're expanding this fundamental definition of a raised to an integer power now to negative powers as well. You're literally multiplying a times itself negative n times here. Or in effect, that's what you're doing. Let's see. Also, if n were equal to 1, a to the minus 1 would be 1 over a to the 1, or 1 over a. A to the minus 1 equals 1 over a. And I'm sure you're familiar with that. You've used it a lot, and you'll continue to use it a lot. But the point I want to make here is how this a to the minus 1 equals 1 over a just falls out naturally from these other laws of exponents. So we have meaningful answers to a to the power of positive or negative integers. What if you had a to the power of the fraction of an integer, 1 over n? What is it? Well, one way to look at that is the following. If you took a to the power of 1 over n, whatever it is, and you raised it to the power of n, and if you believe this property, that means the exponents have to multiply, and you get a to the power of n times 1 over n, which is a to the power of 1, or just a. So in short, a to the power of 1 over n raised to the power of n equals a. So a to the power of 1 over n is the number which, if raised to the power of n, would equal a. And that's just another way of saying that a to the power of 1 over n is the nth root of a. So we'll put that property here. Finally, what about a to the power of m over n? Well, if you believe this property, a to the power of m over n would be a to the power of 1 over n to the power of m, because those exponents would have to multiply to give you this. And a to the power of 1 over n we just deduced as the nth root of a, and that's raised to the power of m. So finally we have a to the power of m over n is the nth root of a to the power of m, and by properties of radicals, that's also equal to the nth root of a to the power of m, where you raise to the power inside the radical. So what do we have here? We started out saying a to the power of an integer was a times itself n times, and now we've advanced to a point where we can say what a to n fractional power is. A to the power of m over n is this. So it's almost like saying we're multiplying a times itself m over n times. It's hard to say what that means, but this interesting equation falls out from the other properties that we've developed. So we can raise a to any fractional power. And in fact, you probably have a feeling that you could raise a to any real power, and although we haven't deduced that from what's in the box, it does turn out to be the case. And really, you have to take some, maybe by Calc 2, you really develop the machinery to deal with that. But we're just going to take it on faith that you can raise a to any real power in this way. So what I'm saying is that for all of the properties we have listed here, even though I said earlier that m and n were integers, they can just be real numbers, and all of these properties hold. So those are the basic laws of exponents, and we use them daily. For some examples, think about 10 raised to the power of 4/3. Well, according to this property, that would be the cube root of 10 to the 4th. And we'll maybe have to take out a calculator there, the cube root of 10, work that out, raised to the power of 4. It turns out to be 21.544 approximately. So if you want to get numeric values for some exponents, you have to use a calculator. But don't rely too heavily on your calculator, because so often you can figure these out in your head. Imagine you had 25 to the power of negative 1.5. Well, negative 1.5 is minus 3/2. So that's 25 to the power of minus 3/2. Use this property, and that power of minus 3/2 comes down to the bottom as a positive. And now we can use this property, 25 to the power of 3/2 is the square root of 25 cubed. And the square root of 25 is 5. So we get 1 over 5 cubed, and that's 1 over 125. So be on the lookout for how many expressions can be simply evaluated just by using these properties. Okay, we're going to move on here. This is just a quick review we've just had of the basic laws of exponents, and hopefully this is old hat. You've seen it many, many times, and you've worked with it. Still, I think when you're starting to do calculus and things are going to get more complex and layered, it's always good to go back to the basics and just review them before you move on, so you can build on it. The next topic I want to talk about today is a thing called an exponential function. An exponential function is a function that has the form of f of x equals a raised to the power of x. where a is a positive constant and it's not equal to 1. We're going to require that a be positive because if a were negative, raising that to a power is problematic, like a negative number to the power of 1/2 is the square root of a negative number. It's not defined. So to remove those ambiguities, we're going to insist that an exponential function have a positive base a. So again, the a is called the base and the x is called the exponent. We also will demand that a not be equal to 1. Otherwise, you just have f of x equals 1 to the power of x, which is just 1. Not very interesting. So let's look at some examples of exponential functions. Our first example is f of x equals 2 raised to the power of x. Let's think about what the graph of that exponential function would look like. We can fill out a chart and plot some points and connect the dots to get a feel for what this graph is. So I've picked some x values from -3 to +3, and we'll work out 2 to the power of x. When x is -3, 2 to the power of -3 would be, let's see, 1 over 2 cubed, and that's 1/8. When x is -2, we have 2 to the power of -2, that's 1 over 2 squared, or 1/4. 2 to the power of -1 is 1 over 2, 1/2. What is 2 to the power of 0? You know from the previous slide, that's 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. So we get this sequence of 7 points here, xy points. And if you plot them, -3, 1/8 would be like right there. And here's the next one, -2, 1/4, -1/2, and then 0, 1 would be here. And if you connect those dots with a smooth curve, it looks like y equals 2 to the x looks something like this. An interesting function, this exponential function. As x increases, it gets fast really, really quickly. It's literally increasing, as we would say, exponentially. When x becomes really big in the negative direction, we have 2 to the power of a negative power. That's 1 over 2 to the positive of that power. That's a very small reciprocal. So as x gets big in the negative direction, 2 to the power of x gets smaller and smaller and smaller, closer and closer to 0. Another example of an exponential function is 1/2 to the power of x. And here I don't mean 1 to the power of x over 2. I mean the number 1/2, whole thing raised to the power of x. That's our base a is equal to 1/2. Let's see what that looks like if we plot it. Well, 1/2 to the power of -3 would be 1 over 1/2 cubed. And if you work that out, it's 8. 1/2 to the -2 would be 1/2 to the power of -2. That's 1 over 1/2 squared. That's 1 over 1/4, which is 4. 1/2 to the power of -1 would be 1/2. Let's see, 1/2 to the power of -1 is 1 over 1/2, which is 2. 1/2 to the 0, well, anything to the 0 is 1. 1/2 to the power of 1 is 1/2. You square 1/2 is 1/2. 1/2 times 1/2 is 1/4. And finally, 1/2 times itself 3 times would be 1/8. 1/2 times 1/2 times 1/2 is 1/8. So for 1/2 to the power of x, for this exponential function, if we plot this sequence of 7 points, it looks like this. So there we go. I'll write this as y equals 1/2 to the power of x, 0.5 to the power of x. So unlike 2 to the power of x, which increased very rapidly, 1/2 to the power of x decreases very rapidly and then starts to stabilize at 0 as x gets bigger and bigger in the positive direction. Now, we're not going to plot points, but you can see how that if you increase the base from 2 to 3, that function would increase quicker because 3 to the power of x is always bigger than 2 to the power of x, at least if x is positive. Y equals 10 to the power of x would look something like this. If you plotted y equals 1.5 to the power of x, well, 1.5 is slightly less than 2. It's no surprise that that graph looks something like this. Here's y equals 1.25 to the power of x. So as that base gets smaller, the exponential function lightens up a little bit. Now here is y equals 1 to the power of x. It's just a horizontal line, y equals 1, because 1 to the power of x equals 1. So it neither increases nor decreases the way the other exponential functions do. And for this reason, we don't allow the base to be equal to 1. We wouldn't really consider y to the power of 1 as an exponential function. But I've put it in here because you can see as the base increases from 0.5 to 1 to 1.25 to 1.5 to 2 and so on, those exponential functions get steeper and steeper and steeper. So there's a whole family of exponential functions, a to the power of x, and we've just graphed a few of them here. But let's think about what's common to all exponential functions. They all have properties. First of all, the domain of an exponential function is all real numbers, because whatever x is, you can raise a positive number to that power by the properties that we had on the previous slide. And you can see that in these graphs, no matter what x is, you have a point on the graph of a to the power of x. However, a to the power of x is always positive, so the output, the domain, is going to be a positive number. And in fact, you can see from these graphs, just reasoning it out intuitively, like looking at 2 to the power of x, you're taking on all positive y values. So the range of an exponential function is the interval from 0 to infinity, all the positive numbers. As we see here, the exponential function a to the x increases if a is greater than 1, increases as you read from left to right, if the base is greater than 1, like 1.25, 1.5, 2, 3, 10, and so on. But it decreases if a is less than 1, between 0 and 1. So for example, here's a is 0.5, that's less than 1. As you go from left to right, this exponential function decreases, goes down. The y-intercept of any exponential function is 1, because a to the power of 0 is always equal to 1. So the y-intercept has to be 1. When x is equal to 0, that's where every single one of these graphs crosses the y-axis, and it happens right there at y equals 1. So y-intercept is 1. And finally, and this is a very important point that I'll leave you with, every exponential function is 1 to 1. If you single out, say, y equals 2 to the power of x, it passes the horizontal line test. It's a 1 to 1 function. So it's going to have an inverse. So that's it for today. We've reviewed exponential functions. Next time, we're going to follow up on the fact that exponential functions are 1 to 1 functions and they have inverses. In lecture 5b, we'll talk about inverses of exponential functions. And those inverses are very interesting and special and important functions. They are called logarithms. So Lecture 5B will be important and significant. I'll see you there. Have a great day, and goodbye.